Hey, alright, this is going to be a short video on something I didn't quite cover last Saturday, but it directly relates to what we talked about max, mins, point of inflections, and f double prime. So, without further ado, this is going to be about concavity. And it is a somewhat relatively, and it's not very, I guess it's kind of important, so yeah, that's why I'm making a video on it. Anyways, so before I talk about concavity, quick review about f prime again. Like this should be the last time I should need to review this. So f prime, what does what does it describe? It describes slope, right? But what is slope? Slope describes whether, or how we view it, or how Calc 1 students mostly view it, is whether the function is increasing or decreasing, right? So right on this area, we see that the function is decreasing. Right here, the function is increasing. So instead of writing slope right now, I'm going to write f prime of x describes whether f of x, the function, is increasing or decreasing. So this basically, derivatives always describe rate of change, and this is a more this is in more layman terms, I guess. So it describes that whether the slope is increasing or decreasing, which basically is the rate of change. So f double prime is the derivative of f prime, so it should describe whether f prime of x is increasing or decreasing. And this is where this is when we talked about how f double prime describes whether the slope is increasing or decreasing. So f prime of x describes whether the function or the graph is increasing or decreasing, and f double prime describes whether f prime of x or the slope is increasing or decreasing. You see how we took the derivative and then we got whether the graph is increasing or decreasing, and then we take the derivative of that, we get whether the slope is increasing or decreasing. So if for some random reason you take the f triple prime, which has absolutely really no use, it will describe whether f double prime is increasing or decreasing, and so on, because that is describing rate of change. And here's a little notation I forgot to introduce to you guys. This is, I believe, Newton's notation. Or no, this might be this. No, this is the other guy's. I forgot his name. Yeah. So this also means f double prime. So this relates to the derivative notation that looks like this. So that's f prime, and if you take the second derivative, this means second derivative. Okay. So f double prime describes whether the slope, or rather f prime of x, is increasing or decreasing. Because when f prime of x describes whether f of x is increasing or decreasing, and when f of x is increasing, that means positive slope. So that's how we say that if this is positive, then the slope is positive because the graph is increasing. Or when this is negative, it is decreasing because, or the slope is negative because the function is decreasing. So applying to this, we talk about whether the slope is increasing or decreasing. Okay, now to concavity. Okay, so if you remember from previous courses what concavity means, concavity just means whether, okay, so this is concave up. This right here is also concave up. Hopefully that jogs in memory. It just describes whether, or in what we learned in pre-algebra or algebra 2 is that concave up basically means that the graph is kind of like a bowl, right? It's like this is concave up, and then concave down is like this, or like this, and where it's kind of like the function is is like expanding outwards, but it's like pointing inwards, kind of like that. So that's concave down and concave up, and that's concave down. So that shouldn't be a new concept to you, but this is where f double prime comes in. So in concave up, what we know about concave up is that the slope is always decreasing. So you see this concave up, the slope is always increasing. I'm sorry. So you see this really negative slope right here, and then it gets less negative, less negative, less negative, and it basically becomes 0. So if this is like a negative 10 slope, this becomes negative 9, negative 8, negative 7, or that's like negative 2, and then like negative a half. So you see how the slope is getting less negative. So the slope is increasing. And remember, we already talked about this in class. If the slope is increasing, f double prime of x is positive. It's going to be positive. Slope increasing. Alright, I'm not even gonna write it. And this is the one side of a concave up, right? Concave up could also look like this, but it's the same deal. They're both concave up. Slope is increasing, but instead of getting less negative, it's getting more positive, right? This could be like a slope of 0, slope of 1, slope of 2, like 0, 1, 2, slope of 5, and like a slope of 10. The slope is increasing, just like this right here. It's getting less negative, but it's increasing. So on all concave up, the slope is always increasing. So what we can conclude from that is that if f double prime of x is positive, I'll write over here, if f double prime of x is positive, then it is concave up. Now, similarly, when we have concave down, which look like this, or like this, slope is always decreasing. So let's say, so you can see that we have some really positive slope here. Let's say 10. That's a less positive slope, but still positive, right? That's like 7, then like 3, then maybe 2, and then 1. So what we see here is that it's getting less positive. So even though they're all positive slopes, it's decreasing. The slope is getting less positive. And then from here, say that's a 0 slope, a negative 1 slope, because now these slopes are negative, right? Negative 2, negative 5, and like negative 10. These are all negative slopes, and so these are getting more negative, and if something's getting more negative, then the slope is decreasing, because obviously negative 10 is much less than negative 1. The slope is decreasing. Similarly, 1 is less than 10. The slope is decreasing as you go on. And remember, we talked about this already. If the slope is decreasing, f double prime of x is negative. So what we conclude from this is that if f double prime of x is negative, then your graph is gonna be concave down, which is relatively easy to remember, because if it's positive, concave up, negative, concave down. So yeah. And here's where it relates to our max-min. If you remember, we developed the second derivative test, and I made a chart for you guys, where if the slope is 0, which would be like right there, and right there, these are 0 slopes, right? Right there and right there. I'll change the color. So like right there and right there. When the slope is 0, then we could have a max or min. We just need to do a second derivative test. And if we check the second derivative test and we find out that f double prime of x is positive, then we know it's concave up. And for concave up, we know it's got to be a minimum. Same for down here. But if we found out the slope of, let's say, I don't know, x equals, so this is like when x equals 7. When x equals 7, the slope is 0. We do the second derivative test. We find out that f double prime of x evaluated at 7 is negative. We conclude that at 7, the graph is concave down. And if it's concave down, then it produces a maximum. Hopefully that makes some sense. Okay, so here we have the graph of f of x, and we want to graph f double prime of x. Now we don't even really need to graph f prime of x to graph f double prime of x, because remember what? So f of x, f of x is the graph, right? F prime of x describes the slope. Oh my gosh. F of x is the graph. F prime of x describes the slope. F double prime of x describes concavity. So when it's positive, you have concave up. When it's negative, you have concave down. Right? So right here, right on this area right here, this is definitely concave down, right? So that means f double prime of x is negative. So concave down, it's got to be somewhere negative. It doesn't matter how negative, we're just drawing a relative graph, right? So it's concave down up until where? Up until right here. This is why I don't like doing online stuff. It's a lot slower. It's a lot easier having classrooms. So you see it's concave down. I'm not even sure if you can see the curvature that easily. I'm gonna change color. Okay, so you see it's concave down up until right there, and then becomes concave up. And we know that when f of x is concave up, f double prime of x is positive. So that means f double prime of x has to cross the x-axis right there. Okay, so it would look like this, because since f double prime of x is negative, we have concave down. But past this point, and let's say that's -2, past -2, f of x becomes concave up. So f double prime of x has to be positive. And that this whole piece is concave up until about right there. Because after that, it goes concave down and then goes concave up again. Oh, sorry, it goes concave up and then goes back to concave down again. See, it's concave down. So it's concave up, so f of double prime concave up, f double prime of x is positive. So we know it's going to be positive like this. And then it's concave down again on this interval right here. It's concave down. Up until where? Up until about, it's hard to see. It's about right there somewhere. And that's what we call an inflection point, by the way. So you see, like, it's concave up, and then I'll try doing a different color again. So this right here is concave up. This right there is concave down. So that's like an inflection point, right? So concave down, concave up, down, up. So inflection point. So back to our graph. Concave down means f double prime of x is negative. So it's got to be negative in this interval. And then past this right here, our inflection point, it becomes concave up again. So if it's concave up again, f double prime of x has to be positive. So this is a relatively rough graph of f double prime of x, but remember f double prime of x describes concavity because it describes whether the slope is increasing or decreasing. And we can use this and apply it to our max, min, and indeterminate forms. So here we have, let's say, that function we used last week. F of x is equal to x to the 4th. So we want to find max and mins. So max and mins, we did this already. So you get the derivative. That's gonna be 4x cubed, and then you want to find when this equals 0. So you set this equal to 0, and you find it's gonna be x is equal to 0. That's because divide by 4, and then you get x cubed is equal to 0, and then you take the third power, and that's gonna be equal to 0. So we know that there's either a max, a min, or a point of inflection at this point, right? So we do a second derivative test, and you take the 3 out 4, so it's gonna be 12x squared, That's the power rule again. Now you evaluate this at x equals 0. And what do you get? You get 0. And remember, when we get 0 for f double prime of x, that means it's indeterminate. If it was a positive, then we know that it's going to be concave up. And when it's concave up, since the slope is 0, it's got to produce a minimum. If f double prime of x becomes negative, it becomes concave down, and that would produce a maximum. Concave down, right? Maximum, concave up, minimum. But it's a 0, so that is our indeterminate form. So what we do is check left and right side of f double prime of x at the point. So we have, the point is x equals 0, right? We want to check points around it. So that could be either negative 0.5 and 0.5, or it could be negative 1 and 1. We just don't want to get too far away from it because you don't know, or usually, yeah, it doesn't, you don't want to get too far away from it because there might be other inflection points and whatnot. But usually finding a relatively easy number to use is ideal. So here I'm going to just use negative 1 and 1 because that's between 0. 0 is between negative 1 and 1, right? So we need to check on the left hand side and right hand side and plug it into f double prime of x. And while we're doing this, we're checking the concavity at those 2 points. So let's do that real quick and I'll show you what happens. So plugging in negative 1 into our f double prime of x. So this is f double prime. This would be 2 primes right there. So plugging in negative 1, so we have our 12x squared. Plug in x equals negative 1, you get 12. You plug in a positive 1, you get the same thing. It's also equal to 12. These are both positive numbers, and these are both f double prime of x evaluated at negative 1, right? You get the idea. These are both f double prime of x. So since we evaluate it at f double prime of x, it describes concavity, right? So that means at negative 1, or to the left of the 0, to the left of x equals 0, it's concave up because it's positive. When we evaluate x equals negative 1 in f double prime of x, which describes concavity, it becomes positive. It means it's concave up. So let's say this is your negative 1. And then here's your 0. That could be either a minimum, a maximum, we don't know, right? So we know to the left-hand side, it's concave up. And then we check the right-hand side, and we found out it's also concave up. So you see where I'm getting at this? So this is your 1, and we know that on the 1, it's also, the function is also concave up. So after checking both sides and finding out they're both concave ups, we can make the we can determine that this is indeed a minimum. And if you graph this, you'll see that if you graph the original function x to the 4th and check x equals 0, you'll see that there is indeed a minimum right there. Let's see a different case. F of x is equals to x cubed now. And we want to find all minimums, maximums, etc., or points of inflection, etc., right? So same deal, take the derivative and make it set it equal to 0, because that's where the slope is 0, and all minimums and maximums have a slope of 0. Okay, so saying this equals to 0, we have 0 equals 3x squared, and then, divide by 3, you get x squared equals 0, and then x equals 0. So this is our critical point. This is our only critical point right here. So second derivative test again. So take the second derivative, which is going to be 6x, and we evaluate it at the point x equals 0. And oh no, we get 0 again. Indeterminate. We don't know if this is a minimum or maximum. So our second derivative test has failed us again. So we have to resort to checking the left and right hand side of x equals 0 at f double prime of x. We need to check to the left and to the right of this. So once again, I'm just going to use the same points, negative 1, which is between 0 and, or 0 is between negative 1 and 1, so I chose these 2 points. You could choose negative 0.5 and 0.5. It doesn't have to be equal. It could be negative 0.5 and 1. Just anything on the left and right hand side of the x value, because x was equal to 0. We want to check 2 points to the left and right of it. So okay, I'm plugging in into our second derivative, 6x, plugging in x equals -1, which is to the left of 0. So here's our, so there's our 0. We don't know what's going on here. We're checking to the left hand side, the -1, and what do we get? We get a -6. Now let's do it. Okay, so before that, let's work with this right now first. So we have a negative number for our f double prime of x. Remember what f double prime of x describes? It describes concavity. So with a negative number, we have concave down. Alright, so to the left of it, it's concave down, because if f double prime is negative, it's concave down. It doesn't matter that the slope is positive. You see the slope is positive here? They're all positive. That doesn't matter with f double prime of x. F double prime of x does not describe slope. It describes concavity. So, yeah, so even though these are positive slopes, it doesn't matter. It's concave down because it's negative. So now we evaluate on the right hand side at the 1. So 6x, evaluate at x equals 1, you get it equal to 6. It's positive, so what we conclude from that is that at x equals 1, this graph is concave up. Concave up. You see what happened here? So you see how to the left of 0, to the left hand side of 0, okay, so to the left hand side of 0, we found out that the graph is negative, the concavity, or f double prime of x is negative, so the concavity is, it's concave down. And then to the right hand side, at x equals 1, f double prime of x is positive, so it's concave up. So we end up getting this right here, and we can see right now that this is indeed a point of inflection. So the slope would be 0 right there. So it becomes, the slope becomes 0. And then it changes to a concave up. From concave down, this region right here is concave down, and this is concave up. So left hand side, right hand side, and so that will determine whether you have a max or min. And we only use this if our second derivative test fails on us, or in other words, we get a 0 when we evaluate the critical points. So it's indeterminate. So we check on the left and right hand side. F double prime of x is check the concavities, the concavity on both sides. Okay, so last quick example of our concavity and f double prime. So here I have a graph. This is f of 1. This is graph x to the 4th divided by 12 minus x squared, and it's the blue one, right? And then I took the second derivative. So I took the derivative and I took the second derivative, and that's going to be x squared minus 2. So you can verify that for yourself. Take f1 and take its derivative, and then take its second derivative. So you get f double prime, and you'll get x squared minus 2. Okay. So we've already talked about how f double prime describes concavity. So this here illustrates that. So looking at f double prime, this red graph right here, you see that it's positive all the way to, if I could just keep it at the pointer, it's positive all the way up till right there. So between -1 and -2, that's when it becomes negative. So looking at this one right here, this blue graph, the f, so this is f double prime, the red is f double prime, this is f. So looking at that point where the red is all positive, so this entire f double prime is positive, we can see that the blue area, or the blue graph, is concave up. But the moment the f double prime becomes negative, so after about, I think that's -1.5, somewhere around there, so after that point, it's all negative, all the way to about between 1 and 2. So that could be 1.2, 1.3, I don't know. So around there, it becomes positive again. But in this region, the red is all negative. And if f double prime is negative, then f is concave down. And we see that this is in fact the case. After this becomes negative, this blue graph, our f, not f double prime, our f, becomes all concave down. Maybe I should just leave the mouse away and just let you look at that yourself, because this is very hard to see if I'm covering it. So you can see that it becomes concave down when the red graph f double prime is negative, and then f double prime becomes positive again past this point right there. I'm using the bottom of the mouse point so it doesn't cover it. There you go. Okay, so when it becomes positive again, when the red graph or f double prime becomes positive again, we see the blue graph, our original f, becomes concave up again. So